In this semester, we study some new concept called modern algebra or abstract algebra. In this, there are some important concepts. In this, here we study theory of groups in this semester. Here I will explain how the concept of groups is developed in a natural way. Here already we know that there are some integers or real numbers, and there is an operation called plus or addition of integers. And what are the properties, well known properties we use in our life, daily life? Here, see this one. 3 plus 7 is equal to 10. Here 3 is an integer, 7 is an integer, 7 is an integer. The result of operating 3 and 7 is again an integer. Here what we call 3 and 7 are operated with respect to plus, or we say addition, and we get an answer that is also an integer. That means belongs to the same set of all integers. And see the second part. Here I am taking three integers, 3, 7, 15. First I am operating, or we say adding 3 plus 7 with bracket and then 15. This gives answer 25. And the other way, first I will add 7 and 15. Then I will add 3. We get the same answer 25. So here first 3 and 7 added, and here 7 and 15 are added. So this equals to the same number here. This is a well-known property in our life. And one more is, I am taking an integer, for example 6. 6 plus 0 gives 6. And here 0 is operated from right side. And here 0 plus 6 is equal to 6. Here 0 is operated from left side. We get the same answer 6. Just I am giving an example. This is true for all the integers, not only 6. Just I am giving an example. So here we are adding 0 from right side and 0 from left side. We get the same 6. And one more is that we see 7 and minus 7 are integers. Here I am operating 7 and minus 7. From right side it is 0. From left side also it is 0. This is true for all the integers, not only for 7 and minus 7. And one more is 3 plus 7 is equal to 7 plus 3. Here first we are taking 3 and next 7. This gives 10. Here first I am taking 7 and next I am writing 3. This gives also 10, same number. So 3 plus 7 is equal to 7 plus 3. These are the known properties in our life. Some mathematicians developed abstract algebra, or we study here groups. Groups is developed on the well-known properties of these, and these properties are generalized to some elements in a set. Not for integers, not for real numbers. We are generalizing these properties for elements in a set. So next we go to the definition of the group. So this is how the groups concept of groups is developed. Next we go to the concept of groups. This is called theory of groups, in which also there are some 5 to 6 chapters, and first chapter is called groups, and we define groups, semi groups, complete groups, like that, and we read some theorems also, or properties we see here. Here first we go to a definition called binary operation. We consider a Cartesian product here. See, let S be a non-empty set. If f is a function from s cross s to s, then f is called a binary operation of s, or binary operation on s, somebody say. So we are taking a s cross s. This is called Cartesian product, and we are defining a function from s cross to s, and this function is called binary operation. I have explained this in a picture way. Here this is a set s cross s, and this is set s. We know that in the set s cross s, elements are denoted by like this, bracket AB, and we are assigning an element x in S. So such f is defined, then f is called a binary operation. We can define one or more binary operations on a set S. And we note some important points regarding this binary operation. For the bracket AB belongs to S crosses, there exists unique x belongs to S such that f of AB is equal to x. So from the definition of a function, we are remembering this point here. There is an element unique image. X is called image. And in the definition of the function, we know that image is unique. F of AB is equal to x and x is belongs to S is an unique element. Next, note. To denote a binary operation, we use symbols star, plus, cross, dot, circle, plus circle, cross circle, dot circle, etc. Here in the definition, I am using a function f, a symbol f. And in general, we know that elements in a set are denoted by English letters A, B, C, D, like that. So we confuse with the elements and f. So for a function, for a binary operation, we use some other symbols like this. F may be considered as an element of the set S. So to avoid confusion, we use symbols for binary operations like this. And one more convenience. Instead of writing star AB, for our convenience, we write like this. Star AB as A star B and circle AB as A circle B. This is our convenience only. We write like this. And we go to some other definition, algebraic structure. A non-empty set G equipped with one or more binary operations is called an algebraic structure. There is set G, equipped means there is a binary operation defined on the set G. Equipped means there is a binary operation defined on the set G. A binary operation, one or more binary operations defined on the set G, then G is called an algebraic structure. And we go to the definition of semi-group. An algebraic structure, bracket S, comma, circle, is called a semi-group if the binary operation circle is associated in S. We write in symbols like this, bracket A circle B circle C is equal to A circle bracket B circle C for all A, B, C belong to S. Here we are considering an algebraic structure S circle. That means S is a non-empty set and circle is a binary operation on S. And this binary operation satisfies this condition in S. In such case, S circle, bracket S circle is called a semigroup. So this is a generalized property of integers. And here S is a non-empty set. So we are generalizing well-known properties in integers to elements of a set. So here such a condition is satisfied in S circle, then S circle is called a semi-group. Next we go to definition of left identity, right identity and identity. What is called left identity and what is called right identity? Let consider bracket S circle be a semi-group. Here directly I am taking a semi-group. That means S is an non-empty set and circle is a binary operation and associated holds good in S. If there exists an element E belongs to S such that E circle A is equal to A for all A belong to S, then E is called a left identity in S. I am searching in S for a particular element E. If there is an E in S such that E circle A is equal to A for all A belongs to S, this must be true for all the elements of S like this property. That means E is operated with A and result is same A. See this one. E is operated from left side with A and the result is same A. In such case, E is called left identity. And one more. If there is an element F belongs to S such that A circle F is equal to A For all A belong to S, then F is called a right identity in S. Here F is operated from right side of A and the result is same A. There is no change. We are getting the result same A. If there is an F with this property, such F is called right identity. Here we are defining left identity and right identity. And next we go to the identity. What is called identity? That means if left identity is same as the right identity, there is only one element which works as left identity and right identity, then it is called identity. We go to the formal definition. If there exists an element E belongs to A such that E circle A is equal to A and A circle is equal to A, then E is called identity in S. Here E works as left identity and E works as right identity, then E is called identity. So in most of the examples and most of the problems, we see there is only element which works as left identity and right identity. There are some examples are there in which left identity is different from right identity, but almost in our class, in this course, we consider all the problems, all the examples in which left identity is same as right identity. Next, we go to some definition. A semi-group with identity element is called a monoid. Just here, a semi-group with identity. That means there is a set associated holds good and identity element exists in such case that bracket S circle is called a monoid. And we go to next left inverse, right inverse and inverse of an element. Let S circle be a monoid with identity element E. Here we are considering a monoid. That means S is a non-entity set, circle is a binary operation. Monoid means associated holds good and unity element exists. And unity element is identity element is denoted by E. Let A belongs to S. If there exists an element X belongs to S such that X circle A is equal to E, then X is called left inverse of A. Here I am taking A belongs, that means A is any element, not a particular element, any element in S. If there exists an X belongs to S such that X circle is equal to E, X circle A is equal to E. Here X is operated with the A from left and we get the identity element E. In such case, X is called left inverse of A. And one more, if there exists an element Y belongs to S such that A circle Y is equal to E, then Y is called right inverse of A. Here Y is operated with A from right side and the result is identity element E, then Y is called right inverse of A. Next we go to inverse. Inverse means left inverse is equal to right inverse. If such a case exists, we call it is inverse element. If there exists an element X belongs to S such that X circle A is equal to E and A circle X is equal to E, then X is called inverse of A. Yes, here X works as left inverse and here X works as right inverse, same element. So in such case, X is called inverse of A. Left inverse is equal to right inverse. In such case, this X is called inverse of A. Left inverse is same as right inverse. So in this class, we have seen definition of a binary operation and symbols we use for binary operations, algebraic structure, semi-group and left identity, right identity and monoid and left inverse, right inverse and inverse of an element. So we have some basic knowledge to define the group. So in the next class, we go to the definition of a group.